Chapter 3 was where we had our introduction to atomic structure. We started off the chapter by looking at the progression of the atomic model and the historical development of each atomic model, from the earliest to the one that we currently have today. So remember that Dalton came up with the solid sphere model. Thomson performed the cathode ray tube experiment to discover electrons and created the plum pudding model. Rutherford did the gold foil experiment to discover the nucleus, that small, dense, positive center of the atom. Bohr used observations and evidence that he found when looking at bright line spectra to conclude that electrons are in specific energy levels that they can move between. And then Schrödinger, among other scientists, in the 1920s came up with the quantum mechanical model, which is very similar to Bohr's model. The only difference is that instead of the electrons existing in a specific location on a given energy level, that the electrons exist in a region of probability we call an orbital. So an orbit in Bohr's model was the electron going on a specific path. An orbital is a region of electron density or a region of probability, where we are most likely to find an electron. So the important thing with the current quantum mechanical model of the atom is that we cannot say with certainty where the specific location of an electron is, just where it will most likely be. This chart summarizes the three main subatomic particles that make up every single atom in the universe, so we should be familiar with their symbol, charge, mass, and their location. Remember that the number of protons is equivalent to an atom's or an element's atomic number, which are the large whole numbers in the periodic table. They're equivalent to the number of protons. That defines or identifies what the element is. Also, for atoms, which are neutral by definition, the electrons are equal to the protons. The mass number for an element is the number of protons and neutrons added together. In this blank symbol here, X represents the symbol of any element. The atomic number, if we're going to report it, is always given in the lower left, and the mass number is always given in the upper left. Now, the atomic number for a given element is going to be the same, but the mass number may vary, and this leads into the idea of isotopes. Remember, isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons, and therefore have different masses. There's different ways to show which isotope we're talking about, and those are all the different ways listed there, giving examples with the three isotopes of carbon. We can list, just like the symbol on the left here, carbon 12 with the 6 below, carbon 13, 6 below, carbon 14 with the 6 below. The 12, 13, and 14 are the mass numbers. We do not need to include the atomic number, like in this row here, because as long as we know it's carbon, we can go to the periodic table and figure out what the atomic number is. The second row here is really the name, how we would read each of the isotopes. So we name the isotope by naming the element and then the mass number. And we can shorten it and abbreviate it using the examples in that first row. So all of those are equivalent to each other. Because isotopes have different masses, we can't say that all carbon has one given mass. So the mass values that are reported on the periodic table are actually average atomic masses, which are the weighted average of the naturally occurring isotopes of an element. So let's take the two most abundant isotopes of carbon, carbon 12 and carbon 13. Carbon 12 has a mass of this many AMU and an abundance of 98.9, where carbon 13 has a mass of this many AMU and an abundance of 1.10. So if we want to calculate the average atomic mass, we take the mass of the specific isotope and we multiply it by the percent abundance, right? How abundant is it in nature? So what that percent abundance means is really that of all of the carbon atoms that exist in the universe, at least here on Earth for the percent abundance, 98.9% of all carbon atoms are going to have a mass of 12 AMU, where 1.1% are going to have a mass of 13.0035 AMU. So we take the mass, multiply it by the percent abundance. We do that with each of the isotopes. And then that will give us our average atomic mass. And if we calculate here, hold on, get rid of one of those zeros there. If we calculate, we should get about 12.01 AMU. And this answer makes sense to us because, remember, it's a weighted average. So the average atomic mass is going to lean closer to the isotope that is more abundant. It's going to weigh heavier to the average atomic mass. So it makes sense there with the data that we were given. We talked briefly about nuclear stability. And there are these two competing forces in the nucleus. We have the strong force that's holding the nucleus together and the repulsive force of the protons wanting to push each other apart. And depending on the number of protons and neutrons that are in there, one will outweigh the other. And if the repulsive force outweighs the strong nuclear force, then the nucleus is unstable and the nucleus will decay to become more stable. And we looked more about how the nuclei will decay in reactions, and we will review that then, but just introducing the idea here that we are talking about isotopes. Some of them are stable and some of them are unstable, and the instability comes from the ratio of protons to neutrons. We then focused really the back end of the chapter on electrons and looking at how we can try and show and notate where electrons are, how many electrons are in each level, and we got more specific as we went on. So a couple of vocab terms to just go over. Ground state versus excited state. The ground state was the lowest energy state for an atom where the electrons are in the lowest energy levels possible, and I gave you some examples there with argon, whether we are listing the energy level or Bohr notation, the 288, that just summarizes how many electrons are in each energy level, or we're doing the SPDF sublevel configuration that's more specific, even, not just saying there's 8 electrons on the second energy level, but 2 of them are in the S sublevel and 6 of them are on the P sublevel. The excited state is when one or more electrons move from the ground state to a higher level. And we can have infinite possibilities of what an excited state configuration looks like, but as long as we have an electron moving from a lower energy state to a higher energy state, it's considered an excited state configuration. The valence electrons are the electrons that are on the outermost energy level of an atom, and I show you there again with the argon example. Ions is if an electron is lost or gained to the valence shell, then we create an ion. So atoms are neutral, protons equal electrons, but if they start gaining or losing electrons and we throw off the balance of protons and electrons, then we have an ion. Anions are negative, they have gained electrons, have more electrons than protons. Cations are positive, they have lost electrons and then therefore have more protons than electrons. We looked at bright line spectra and we looked at flame test for sort of what Bohr used as his observations and the impetus for coming up with his model. Putting different elements into a flame, we looked at that certain metal elements give characteristic colors. Sodium gives a yellow color, potassium gives a violet color, strontium gives a red color. But those colors are not the full story. If we use a spectroscope to take that color and split what colors make up that one color we are seeing with our eyes, we get something called a bright line spectra, which are individual bands of energy, individual bands of color that are being given off by a specific element. And each element has a characteristic bright line spectra that we can use to identify an element, sort of like a fingerprint. We focused on electron configurations. Again, here are some different ways in which we can write or report electron configurations. We have an SPDF configuration and then an orbital configuration. So these two are showing the same thing, just in different ways. This orbital configuration is more specific because it's showing me whether the electrons are paired in the orbital, right? And that here in the 2p orbital, I have 3 electrons, but they're all separate. So those are just 2 different ways to report electron configurations that we should be familiar with. Here's a chart that summarizes on each energy level how many sublevels there are, how many orbitals are in each sublevel, a periodic table to accompany that, and a diagram to show the filling order. Remember that we are following Aufbau's principle, which fills the lowest energy orbitals first, but that's not always sequentially. So if we look from the periodic table, remember we use the periodic table to help us write out the configurations. It starts with 1s, and then we go 2s and 2p, and then 3s and 3p, but then we fill 4s before we fill 3d, and then go back to 4p. So we should be familiar with that, the filling order. We should be familiar with the shapes of the sp and d orbitals. The f's are a little weird, but sp and d we should be familiar with. We focused on, the only other thing really I guess we focused on in this chapter was calculating the energy involved in an electron transfer. So if an electron falls from one energy level to another, it's giving off energy. How much energy in joules is it giving off, and what does that correspond to? Are we going to see it as a color, or is it going to be in the infrared or ultraviolet range and we won't see it? So we talked about the electromagnetic spectrum a little bit, correlating the energy of the wave to the frequency. So high frequency meaning high repetitions, and how many wave cycles per second means higher energy. We're going to get that when the wavelengths are short. If we have longer wavelengths, then the frequency is going to be lower because I'll have to wait longer for the wave to repeat. That corresponds to lower energy. And then we used these equations. E is equal to h nu and c is equal to nu times lambda to calculate frequency, to calculate wavelength, to calculate energy of a wave. We have constants that you will be given if you need to use them to calculate, but you should know how to use these equations and when you would use them given certain data. This wraps up the summary for Chapter 3, and you should be ready to take your Chapter 3 throwback quiz.